Restarting the recording. All right. All right, it won't let me clear previous handouts on the document, so I've restarted the recording. Let's look at what I have page 4 for a moment, and I'll start to talk about operators. Okay. You all know that a function changes a number to another number. For example, if f is x squared, you push a 2 into f, and out comes a 4. You push a 3 into f, and out comes a 9. Operator changes a function to another function. So if you have an operator O, and I'll put a hat on it, you can often tell an operator by its hat. You push some function f into O, and some function g pops out. Now, every physical observable in quantum mechanics has an operator, a corresponding mathematical operator. For example, in one dimension, there is a position operator x, which means simply multiply by x. Momentum operator is a little trickier. It's often written p with a hat, but it's h bar over I d dx. Okay, so for example, let's let the operator p operate on x squared. Okay, now what I just wrote illustrates one of the important points about operators, which is that the operator looks to the right. So x squared is to the right of p, so p is going to operate on x squared. Now the particular form of this operator is h bar over I, which is just a constant for our purposes. Don't worry about the I right now. And then it's d dx, which means take the first derivative. Okay, so this is the first derivative operator multiplied by a constant. Okay, then we all know that if you take the first derivative of x squared, it's 2x. So the answer would be 2h bar over I times x. Now the kinetic energy operator in quantum mechanics is essentially the second derivative operator multiplied by the constant h bar squared over 2m, where m is the mass of whatever particle you're talking about. Here we have a kinetic energy particle for one operator in one dimension. Trying to delete some of the stuff on the right-hand side. So if whatever reason F is x squared again, the kinetic energy operator is often K with a hat. If F is x squared again, you could take K, F, and that would be h bar squared over 2m times the second derivative of h squared of x squared, which is just 2. So this operator and this function actually just produces h bar squared over m, for example. For any potential energy function, the corresponding operator is just that function. So it sort of looks like the position operator that way. Don't need that. I don't need that. The Hamiltonian is K plus V, or whatever the kinetic energy operator is, K hat plus V with a hat. Okay. It's 11 o'clock, and today, for whatever reason, I'm having technical difficulties. So I want to begin by talking about some more about operators, a little bit about wave functions as you've seen, and then I'll come to this model system where we start to show how some of these ideas come together. That will happen Tuesday when hopefully all of Collaborate's technical issues will disappear and will be taken care of. Okay. Questions before I sign off?